Welcome Tashians to Sleep By. Tonight, let's let go of everything that feels certain. Let's step beyond what's familiar, beyond the walls of logic, beyond the boundaries of common sense, because the deeper we look into the universe, the less it behaves like the one we think we know. Particles flicker in and out of existence, matter dissolves into waves of probability, and the fabric of time itself begins to blur at the edges. This is the world of quantum physics, a place where the impossible becomes normal, where things can exist in two states at once, and where simply looking at something can change what it becomes. Einstein called it spooky action at a distance. Niels Bohr called it beautifully irrational. And tonight, we call it an invitation to drift into the mystery that underlies everything. So, take a deep breath. Let the noise of the day fade behind you. Let curiosity guide you into the quiet strangeness that pulses at the heart of reality. Because what you're about to discover is that the universe doesn't just bend the rules of logic, it rewrites them entirely. This is Science to Sleep By. And tonight, we fall together into the dreamlike truth of how quantum physics destroys common sense. Common sense is our oldest companion. It's the quiet voice that tells us what is real, what is safe, what is stable. It guides the way we move through the world, the way we expect a glass to shatter when it falls, or how we know the sun will rise again tomorrow. It's the invisible rulebook written by evolution, honed by experience, and strengthened by familiarity. For most of human history, it has been our anchor in a universe that often feels too vast to understand. When we stand in our kitchens, touch a wooden table, or watch the rain slide down a window, we rely on the certainty that objects are solid, that time moves forward, and that causes precede effects. Everything seems beautifully simple. The world behaves, for the most part, exactly as our senses say it does. But common sense was built for survival, not for truth. It evolved in a narrow band of existence, the world of medium-sized things, trees, rivers, stones, and stars in the night sky. Our instincts were shaped by what we could see and touch, by what helped us hunt, gather, and build shelter. The laws we learned from experience, gravity, motion, heat, made perfect sense in that world. They still do. If you drop an apple, it falls. If you turn on a light, the room glows. If you speak, your words ripple through the air. To our eyes, the universe is solid, mechanical, and consistent, and yet, beneath that calm surface lies another reality, one that defies every lesson our senses have ever taught us. The closer we look, the more our everyday logic begins to crumble. But before we dive into that strange quantum sea, it's worth pausing here in the comforting shallows of common sense to appreciate how extraordinary it is that our minds can even make sense of the visible world at all. Think of how effortlessly we predict what comes next in our daily lives. When we open a door, we know the room behind it will still be there. When we toss a ball, we know it will arc and fall back to earth. This predictability forms the rhythm of our reality. It's the silent contract between mind and matter, the expectation that what we see, touch, and remember will remain stable. But stability is an illusion, one created by the limits of perception. Imagine holding a smooth pebble in your hand. It feels solid, weighty, whole. But science tells us that pebble is mostly empty space. Its atoms are tiny worlds, each with a dense nucleus surrounded by clouds of energy that barely touch one another. The solidity you feel is not because matter is solid, but because of the electromagnetic forces repelling your hand. Your sense of touch is a dialogue between invisible fields. The pebble isn't a solid object at all, it's a shimmering storm of probabilities, frozen in your perception. Our common sense can't grasp that. It was never built to. It sees a rock, not a probability cloud. It sees permanence, not the restless dance of subatomic particles flickering in and out of existence. The human brain evolved to find patterns, not paradoxes. It's designed to smooth over the chaos, to construct a world that feels predictable enough to survive in. This comforting illusion has served us well for millennia. It allows us to build bridges, write music, fall in love, and trust the ground beneath our feet. Without it, the world would be unbearable, a constant storm of uncertainty. Common sense creates order, and in doing so, it creates meaning. It tells us who we are, and what kind of universe we live in. And yet, the deeper we've explored reality, the more this trusted companion has begun to falter. The first cracks appeared when scientists looked closely at light. Was it a wave or a particle? Experiments said both. That made no sense. Then came atoms. Indivisible, or so we thought until we found smaller particles within them. Then those particles began to behave in ways that defied every rule of classical physics. The more we studied them, the less logical they became. It's almost poetic that our greatest tool, reason, leads us to a realm where reason no longer applies. What we discover there challenges everything we believe about the world. Objects can be in two places at once. Particles can vanish and reappear. Observation itself can change what is real. Time can bend, reverse, or stretch, depending on where you are. The universe that common sense promised us tidy, linear, and predictable begins to dissolve into something much more mysterious. But this first step, acknowledging how deeply common sense is woven into us, is essential. Because to understand how quantum physics destroys common sense, we first have to see how deeply it built us. It's not just a way of thinking. It's the very foundation of our mental stability. When we look up at the stars, we feel awe precisely because they seem fixed and eternal. When we drop something and it falls, we feel reassured by gravity's consistency. Common sense isn't just logic, it's emotional comfort. It's the feeling that the world can be trusted. And that's why what comes next feels so unsettling. The quantum world doesn't care about trust or comfort. It doesn't follow the paths our intuition lays out. It doesn't obey the rules that made our ancestors safe. It exists beneath the floorboards of our perception, where logic fails and probability reigns. But before we descend into that strangeness, it's worth taking one last slow breath in the world that makes sense, a world of cause and effect, of solid ground and certain outcomes, of doors that stay where we left them, and apples that fall when dropped. Because soon, that sense of order will begin to flicker. The closer we look, the less the world will resemble the one we thought we knew. And the more we will have to question whether common sense ever described reality at all. No, we begin to leave behind the gentle, predictable landscape of everyday life. The place where gravity feels faithful, where time keeps its steady rhythm, and where cause and effect walk hand in hand. We descend instead into the quantum realm, a domain so small that the rules of normal existence simply stop working. It is here that logic begins to bend, where our language strains to describe what we find, and where reality itself seems to shimmer with contradiction. This is the hidden foundation of everything that exists. Every atom in your body, every star in the sky, every grain of sand on the shore. And yet, the laws that govern it feel alien to everything we know. When we peer into this microscopic world, we no longer see solid matter. We see patterns of energy, vibrating fields, and mathematical possibilities. A single electron is not a tiny marble spinning around a nucleus. It is a cloud of potential, a ripple in a field that extends everywhere. It doesn't have a definite location until we measure it, until we look. Before that, it exists in a strange in-between state, both here and there, both real and unreal. This is the heart of quantum physics, a world not of certainty, but of probabilities. The equations that describe this world don't tell us where something is, they tell us where it might be. That alone overturns everything common sense has ever taught us. In our everyday lives, we expect things to exist whether we're looking at them or not. A tree stands in the forest even when no one sees it. A rock remains on the ground whether we watch it or not. But in the quantum world, that assumption dissolves. Particles exist as waves of possibility until observation forces them to take a single form. To look is to choose not consciously, but physically. Measurement changes the outcome. Imagine a single photon, particle of light, traveling through space. In classical physics, it would follow a clear path from point A to point B. But in the quantum realm, the photon takes every possible path at once. It explores all trajectories simultaneously, interfering with itself like ripples crossing a pond. Only when we detect it, when our instruments say, "There, that's where it is," does it settle into one reality. Until that moment, the photon exists in a haze of potential. This idea is so radical that even Albert Einstein, who helped give birth to quantum theory, refused to believe it fully. God does not play dice, he said, but the universe, it seems, plays dice constantly, and we are just beginning to notice. The deeper scientists looked, the stranger things became. Particles could behave like waves, and waves could behave like particles. An electron could pass through two slits at once, as if it were in two places at the same time. When we observed it, the act of watching made it choose one path, as if reality itself responded to being noticed. Experiments repeated again and again confirmed this eerie truth. Observation changes what happens. It is not simply that we discover reality. In some subtle way, we help shape it. Logic begins to fracture here. How can something exist and not exist at the same time? How can the simple act of looking alter the fundamental nature of matter? The human mind, built for macroscopic stability, trembles at this paradox. We search for metaphors. Waves on an ocean, dice rolling through space, strings vibrating in multiple dimensions, but each image only partly captures the quantum mystery. The truth seems to live somewhere beyond our intuition, in a language the universe understands, but we barely speak. If we could shrink ourselves down to the scale of an atom, nothing would appear as it does above. There would be no color, no texture, no fixed boundaries. The space between particles would be vast, the emptiness echoing like a cosmic cathedral. Electrons would not orbit neatly like planets, they would blur into clouds of probability, sometimes appearing, sometimes vanishing. The concept of position, of solidity, of sequence would lose meaning. A quantum world is not a collection of things. It is a web of relationships, a continuous field where events emerge rather than exist. And this is where logic fails. Our minds crave boundaries and causes, beginnings and endings. But quantum physics reveals a universe that is inherently uncertain. The closer we look, the less definite it becomes. It's as if reality is a vast ocean of potential, and what we call existence is only the surface, a momentary ripple formed when energy meets awareness. The rest, the deeper truth, is a wave that stretches across time and space, infinite and unknowable. For scientists, this uncertainty isn't a flaw. It's the feature that allows everything to exist. Quantum indeterminacy gives rise to the stability of matter, the formation of atoms, the glow of stars. It's the randomness at the heart of creation. Without it, there would be no chemistry, no life, no universe. The unpredictability of particles builds the predictable world we see above. The irony is breathtaking. From chaos, order emerges. Still, even with a century of experiments and theory, no one can fully explain what the quantum realm means. We can describe it mathematically with exquisite precision. Quantum mechanics predicts outcomes more accurately than any other scientific theory in history, yet its implications remain beyond human reason. The numbers work, but the picture they paint makes no sense to our intuition. We can calculate, but we cannot comprehend. Physicist Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." That sentence isn't a confession of failure. It's a recognition of humility. The quantum world doesn't exist to satisfy our understanding. It simply is. It doesn't ask for logic, and it doesn't apologize for mystery. In this realm, certainty dissolves. A particle's position is not fixed. Its energy not absolute. What we call reality is a mosaic of possibilities, woven together by chance and observation. Every moment you exist, every breath, every flicker of thought is rooted in this strange dance of probability. Beneath the floorboards of your perception, the world flickers in and out of existence, guided not by reason, but by randomness. To enter the quantum world is to step into a landscape where the familiar laws of nature twist into riddles. Up is down, cause is effect, and observation becomes creation. Here, it doesn't just fail, it dissolves completely, leaving only wonder behind. The deeper you look, the more the universe seems to whisper that what we call reality is far stranger, far softer. and far more alive than we ever imagined. There are moments in the history of science that shake the foundations of how we think about the universe. The double-slit experiment is one of them, a deceptively simple setup that revealed one of the most profound and unsettling truths ever discovered. It is not just an experiment. It is a mirror held up to reality, showing us that the world behaves differently when we are not looking. To understand how quantum physics destroys common sense, we must walk slowly through this experiment, because within it lies the heart of the mystery. The moment when reality seems to choose what to be. Imagine a darkened laboratory. A thin metal plate stands upright, pierced with two narrow slits side by side. Across from it sits a screen that can record where particles land. You take a beam of light or light, electrons, or even atoms, and you aim it toward the slits. Classical logic tells us what to expect. If particles are like tiny bullets, each one will go through one slit or the other and hit the screen behind it, forming two bright bands aligned with the slits. It's simple, direct, and makes perfect sense. But that is not what happens when the beam is turned on and no one observes which slit each particle passes through. Something extraordinary appears on the screen. Instead of two neat bands, a pattern of many thin, alternating light and dark stripes emerges, an interference pattern, the hallmark of waves overlapping with each other. This is what you'd expect if the particles were behaving like ripples on water, spreading out, passing through both slits at once, and interfering with themselves. But how can something solid, like a particle, go through two slits at once? How can it be in two places at the same time? It's as though each particle splits into 1,000 versions of itself, explores every possible path, interferes with its own shadow, and then reforms on the screen as a single dot, part of a grand pattern that only appears when many such events are combined. This is the mystery of wave-particle duality, light and matter behaving as both waves and particles, depending on how we look at them. But the strangest part comes next. When scientists decided to check which slit the particles actually went through, they placed detectors beside each slit to observe the path. The moment they did, the interference pattern vanished. Instead, the particles behaved exactly as common sense predicted. Two neat bands appeared. Just by observing, the outcome changed. The act of measurement of watching forced each particle to decide on one path, collapsing its wave of possibilities into a single, definite state. The observer didn't merely record reality, the observer participated in creating it. This was not a one-time fluke. The experiment has been repeated countless times, with light, electrons, even large molecules containing thousands of atoms, and the result is always the same. When unobserved, matter acts as a wave of possibilities. When observed, it becomes a particle. It is as if reality exists in a dreamlike haze until someone looks, and only then solidifies into something tangible. This defies everything common sense tells us. In our daily lives, objects don't wait for us to notice them before deciding where they are. A coffee mug on a table doesn't hover between positions, waiting for an observer to collapse its possibilities. But at the quantum level, this is precisely what happens. The universe behaves like a story being written as it's read. The words exist as potential until the reader's eyes pass over them, and only then do they take on form. The implications are staggering. If observation shapes outcome, what is the role of the observer? Are we by the very act of perceiving shaping reality itself? Quantum physics doesn't answer this directly. It only tells us what happens, not why. Some interpretations, like the Copenhagen interpretation, suggest that reality remains undefined until measured. Others propose that all possible outcomes exist simultaneously in branching universes, that each possibility is realized somewhere, in some version of existence. And yet others hint that consciousness itself plays a role. That awareness is somehow woven into the structure of the cosmos. Whatever the explanation, the double-slit experiment tells us that the line between object and observer is far thinner than we ever imagined. The universe is not a machine that grinds away independently of us. It is a dynamic interplay of possibilities that solidify in relation to observation. The more we look, the more the boundary between out there and in here begins to blur, Think about this carefully. When a single electron is fired toward the slits, it seems to sense the entire setup. It doesn't just go through one opening blindly. It knows whether both slits are open because the interference pattern depends on that knowledge. How does it know? The electron behaves as though it explores every possible path, as if it has awareness, not consciousness in the human sense, but a kind of universal sensitivity built into matter itself. It's as though reality contains memory, awareness, and choice, qualities we once believed belonged only to living things. This experiment doesn't just challenge science. It challenges philosophy, perception, and the meaning of existence itself. It invites a deeply unsettling possibility that reality isn't fixed but fluid, a participatory event rather than a static fact. The world doesn't exist as a complete picture waiting to be observed. It exists as a set of potential pictures, and observation paints one of them into being. The double-slit experiment also humbles us. It reminds us that our sensory experience, the one that tells us the world is solid, definite, and predictable, is a limited translation of a far deeper, more elusive truth. Beneath the surface, everything is uncertain until interaction gives it form. We are participants in a universe that seems to know it's being watched, and yet, this experiment is not mystical in origin. It is physics, verified by rigorous testing. It sits at the heart of technologies we use every day. Quantum mechanics powers the microchips in our phones, the lasers in our devices, the MRI machines in our hospitals. The same mysterious principles that defy logic are the ones that drive modern civilization. The double-slit experiment isn't just an abstract curiosity, it is the foundation of the world we live in. To truly grasp its meaning, imagine turning off the detectors again. Once more, the interference pattern appears. The universe returns to a dreamlike state, where everything possible happens at once. The moment we stop watching, the particles resume their dance of uncertainty, free from the constraints of observation. It's almost as if the act of not knowing allows the universe to breathe, to express its infinite possibilities without being forced to choose. The double-slit experiment whispers something profound, that reality is not a solid structure, but a fluid performance, unfolding moment by moment in response to the awareness that beholds it. What we call the physical world is not separate from us. It's a conversation between what exists, what could exist, and the mysterious act of observation that bridges the two in the soft glow of quantum uncertainty. One of the most beautiful and bewildering concepts emerges: superposition. The idea that a single particle can exist in multiple states at once until it is measured. To our everyday minds, this sounds impossible. How can something be here and there, up and down, moving, and still at the same time? Yet, at the quantum level, this isn't a fantasy, it is the fundamental way the universe behaves. Every atom, every electron, every photon you see, and even those you don't, are not fixed in a single state. They exist as overlapping probabilities, layered realities, coexisting possibilities waiting for a moment of observation to collapse into one. To imagine superposition. Picture standing before a still pond at dusk. The surface is calm, reflecting the fading light of the sky. You drop a single pebble into the water, and ripples spread outward in perfect circles, overlapping and intersecting with themselves. That delicate interference, that simultaneous existence of many wavefronts, is not far from what happens inside an atom. Each particle, like a pebble, generates waves of possibility that spread through the quantum field. Those waves represent every potential state it could occupy, every possible position, energy, spin, or direction. The universe does not choose one until observation demands it. In the macroscopic world, we cannot see this directly, because the effects of superposition fade quickly as systems grow larger. The world of tables, trees, and human bodies is too noisy, too entangled with countless interactions to maintain the delicate balance of quantum states. But in the quiet, microscopic realm, where isolation and precision can be achieved, superposition is not only observable, it's measurable. Physicists have watched atoms exist in two energy levels at once, photons taking two paths simultaneously, and even molecules made of hundreds of atoms suspended between multiple configurations. The universe, it seems, prefers to hold its options open. Perhaps the most famous illustration of this idea is the thought experiment known as Schrödinger's cat, proposed by Austrian physicist Erwin Schrödinger in 1935. He imagined placing a cat inside a sealed box with a vial of poison that would be released if a single radioactive atom decayed. According to quantum mechanics, until someone opens the box to check, the atom exists in a superposition of decayed and undecayed states. And since the cat's life depends on the atom's state, the cat too exists in a superposition both alive and dead at the same time. Only when the box is opened, when observation takes place, does the wave function collapse and the cat becomes one or the other. Schrödinger's point was not to suggest that cats actually exist in such limbo, but to show how absurdly different quantum logic is from human logic. In the quantum realm, nature holds all possibilities in suspension, as if reality itself were waiting to be observed into existence. The implications of superposition ripple through every aspect of existence. It challenges the notion that the world is deterministic, that given enough information, we could predict everything that happens. Quantum physics says no. Even with complete knowledge of a system's wave function, we can only predict probabilities, never certainties. Reality is not a film already printed on the reel. It is more like a live performance, unfolding moment by moment, where every outcome exists as a potential until the act of measurement chooses one. If we pause to reflect on what this means, the universe becomes almost dreamlike. Imagine that every electron in your body, and there are about 1027 of them, exists in overlapping states, a vast web of intertwined possibilities. The world you perceive as solid and continuous is, at its foundation, symphony of unresolved choices. It is as though existence itself is composed of chords rather than single notes, harmonies of potential vibrating until consciousness or interaction strikes the final key. Superposition also carries a deep philosophical echo. It tells us that the limits we perceive, the division between what is and what is not, may not exist in the fundamental structure of nature. The universe doesn't seem to recognize either or. Instead, it operates on both and. A particle is both here and there, both a wave and a particle, both existing and not existing until its potential is resolved. That duality, or rather, that multiplicity, underlies everything that makes up the physical world. Scientists have pushed this phenomenon to extraordinary extremes. In laboratories, particles have been placed in superposition for remarkable durations, even in systems large enough to be visible under a microscope. Quantum computers, one of the most promising technologies of the century, depend entirely on superposition. While a classical computer bit can exist only as a 0 or a 1, a quantum bit, or qubit, can exist as 0 and 1 simultaneously. This allows quantum computers to perform calculations that would take ordinary computers millions of years, solving problems not by choosing one path, but by exploring all possible paths at once. It is a practical demonstration of superposition, an engineering miracle born out of the strange logic of quantum physics. But the most haunting question remains unanswered. What exactly causes a superposition to collapse? What transforms the wave of probabilities into a single observed state? Is it interaction with the environment? What physicists call decoherence? Is it the act of measurement? Or is it something deeper, something tied to the very act of consciousness itself? The question draws a faint, provocative line between physics and philosophy, between the measurable and the unknowable. When we observe, we don't merely see what is, we help define it. The universe and observer are not separate entities. They seem to be part of one continuous process, dancing in and out of definiteness together. To think that every atom in your body might exist in countless superposed states before coalescing into the physical form you call you is both humbling and uplifting. It means that at the most fundamental level, existence is flexible, fluid, and full of possibility. It is not a rigid machine grinding through preordained outcomes, but a living tapestry of potential, responsive, adaptive, and infinitely creative. Superposition reveals that reality is not a single, static truth. It is a field of maybes, each one alive until the universe decides, through observation, which one will come true. At night, when you look up at the stars, remember that the light reaching your eyes began its journey long before you were born. Photons traveling for thousands, sometimes millions, of years. Each photon existed in superposition, a wave of infinite possibilities, until it encountered you. The act of your eyes catching that light collapses its journey into a single history, a single path through the cosmos. In that moment, you and the universe meet, and the potential becomes real. If superposition shows us that a single particle can exist in multiple states at once, then entanglement reveals something even more astonishing. That two particles can become linked so completely that what happens to one instantly affects the other, no matter how far apart they are. It is a bond so deep, so inexplicable, that even Einstein himself called it spooky action at a distance. In the quiet, infinite fabric of the universe, entanglement is the invisible thread weaving everything together. An intimate connection that defies the limits of space, time, and common sense. Imagine two particles born from the same event, perhaps a photon splitting into a pair of twins. From that moment on, their quantum properties become intertwined. You can separate them by inches, miles, or even galaxies, and yet they remain connected in a way that transcends physical distance. Measure one, and the other responds instantly. It is as if the universe refuses to let them forget that they were once one. In a world governed by relativity, where information cannot travel faster than the speed of light, entanglement appears to break every rule. And yet, it has been tested and confirmed again and again. Its reality is undeniable as it is incomprehensible. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, proposed what became known as the EPR paradox. They believed that quantum mechanics must be incomplete. The idea that two particles could affect each other instantaneously across vast distances seemed absurd, a violation of locality and causality. Two pillars of physics. They argued that there must be hidden variables at play, unseen factors that explained the strange correlations between entangled particles without invoking faster-than-light communication. In their view, quantum mechanics worked, but it couldn't possibly describe the full story. Decades later, in the 1960s, physicist John Bell devised a way to test this idea through what are now known as Bell's inequalities. If hidden variables existed, the correlations between entangled particles would obey certain statistical limits. If they didn't, if the particles were truly connected in the quantum sense, those limits would be violated. When the experiments were performed, the results were unambiguous. The inequalities were broken. Reality, it seemed, was non-local. Entanglement was real. The universe did not care about our demand for separation. To grasp what this means, think of two coins spinning in the air. You can't see whether they'll land heads or tails until they fall. But if those coins are entangled, something extraordinary happens. The moment you look at one and see heads, you instantly know the other must show tails, even if it's on the other side of the universe. It's not that information travels between them, it's that their outcomes were never independent to begin with. In some deep, invisible way, they share a single quantum state. They are not two objects, but two expressions of the same underlying reality. This is not just theory, it has been demonstrated repeatedly in laboratories. Photons have been entangled and separated by kilometers, yet when one's polarization was measured, the other responded instantaneously. The same has been done with atoms, electrons, even small molecules. No matter the distance, their behaviors remain correlated beyond any classical explanation. It's as though the universe itself knows how to stay in touch, no matter how far it stretches. For centuries, physics painted a picture of the universe as a grand machine, predictable, local, and composed of separate parts. Entanglement shatters that image. It tells us that the world is not made of isolated pieces, but of relationships. That separation is an illusion, and the deeper truth of existence is connection. Every particle, every field, every moment in time is woven together in a cosmic web of interaction. What happens here can echo there, not through signals or force, but through the fundamental unity of existence. Some physicists describe entanglement as the very fabric of reality itself. Recent theories even suggest that space and time emerge from networks of entangled particles. In this view, what we perceive as distance is an illusion created by degrees of entanglement. The closer two systems are in the quantum sense, the more connected they are, and the less space exists between them. The cosmos, then, is not a vast empty void, dotted with matter, but a single, inseparable field of relationships, a universe that knows itself through connection. The philosophical implications are staggering. If everything in the universe is entangled at some level, then perhaps nothing is truly independent. Every thought, every atom in your body, every photon of light from a distant star might be part of an ongoing conversation that transcends physical boundaries. The air you breathe could be entangled with the first atoms born after the Big Bang. The quantum threads connecting particles are so delicate and omnipresent that, in a sense, we are all participants in one continuous cosmic interaction. Entanglement has also become the beating heart of modern technology. Quantum encryption, quantum teleportation, and quantum computing all rely on this strange property. In quantum teleportation, for instance, information about a particle's state can be transmitted across distance without the particle itself traveling. It's not teleportation in the science fiction sense. Nothing physical moves, but the state, the very essence of the particle's identity, reappears elsewhere through entanglement. In quantum networks, pairs of entangled photons can transmit information with perfect security because any attempt to intercept the message would instantly disturb the entangled state, revealing the intrusion. The same spooky action that puzzled Einstein now forms the foundation of a new technological era. Yet beyond the mathematics and the machinery, entanglement carries an emotional resonance that's hard to ignore. It whispers something profoundly human. That connection is not just a metaphor but a law of nature. When two people meet, when hearts align, when ideas echo across minds, we often describe it as being in sync or connected. Perhaps the universe operates on the same principle. From the smallest particles to the largest galaxies, we are not separate observers staring out at a distant cosmos. We are expressions of its entangled state, ripples in the same quantum sea. If we could see this truth directly, if our eyes were attuned to the delicate threads of entanglement, we would see the world as a luminous web, shimmering with connection. Every leaf, every raindrop, every star would be bound by invisible lines of relationship. The space between us would not be empty. It would hum with the quiet vibration of unity. Entanglement reveals that distance is an illusion of perception. What looks divided from one angle is, at a deeper level, a single unfolding pattern. To live in a universe of entanglement is to live in a universe where everything touches everything else, where the faintest action reverberates through the whole. It means that the story of existence is not a collection of separate events, but one continuous motion, a symphony of intertwined possibilities played on the grand instrument of the cosmos. As we continue to drift deeper into the quantum realm, we encounter a concept that seems to twist the very fabric of reality itself: time. In our everyday lives, time flows steadily forward. Seconds tick into minutes, minutes become hours, and the past is fixed while the future is unknown. Cause precedes effect. The sun rises before it sets. Our memories are anchored in what has already happened, and our expectations stretch toward what is yet to come. This orderly sequence forms the backbone of common sense, giving us the comfort of continuity, the illusion that reality is predictable. Yet, at the quantum level, time is not so straightforward. Quantum physics suggests that the arrow of time, the sense of past, present, and future, may not be a universal law, but an emergent property. In other words, the progression of events that we perceive may arise from statistical patterns rather than an absolute flow. Particles at the quantum level do not always adhere to a strict chronological order. Some processes can occur in ways that seem to allow the future to influence the past, where causality appears flexible and events are linked in a subtle web rather than a straight line. Experiments in quantum mechanics have hinted at these possibilities, challenging the notion that time is the immutable river we thought it to be. One of the most striking illustrations of this comes from experiments involving entangled particles. When two particles are entangled, the measurement of one instantaneously determines the state of the other. But what happens if the measurements are separated, not just by space, but by time? In some cases, it seems that a choice made in the present can influence the outcome of a particle in the past, a phenomenon that seems to violate our intuitive understanding of cause and effect. This is not just science fiction. Laboratories have conducted experiments where decisions made at one point appear to retroactively affect the behavior of particles that were measured earlier. The results are subtle, probabilistic, and carefully controlled, yet they challenge the very notion of temporal order. Consider the famous delayed choice experiment, proposed by physicist John Archibald Wheeler. In this thought experiment, a photon passes through a series of paths toward a detector. Whether it behaves as a wave or a particle depends on a measurement choice made after the photon has already entered the apparatus. Astonishingly, the photon seems to decide how to behave based on a future event, as though it reaches backward in time to reconcile the conditions. The experiment does not violate quantum theory, it confirms it. Yet to our common sense, it is profoundly counterintuitive. The cause no longer strictly precedes the effect. Time becomes flexible, a tapestry where threads can intertwine in ways that defy linear logic. Quantum mechanics also raises questions about temporal uncertainty. Just as particles exist in superposition, occupying multiple states until observed, time itself may exist in a similar quantum haze. The precise moment at which an event occurs may not be fixed until it is measured. From the perspective of an electron or a photon, the distinction between before and after may be meaningless. Only when observation or interaction occurs does time crystallize into a sequence that humans can perceive. Our experience of past, present, and future may therefore be a construct imposed by consciousness, a narrative shaped to make sense of a fundamentally fluid reality. This perspective reshapes our understanding of causality, one of the pillars of human logic. In classical physics, causality is absolute. A causes B, B causes C, and so on. But in the quantum world, causality is not always so simple. Effects can appear to precede their causes, correlations can exist without direct interaction, and entangled particles exhibit behaviors that transcend linear explanation. The universe, it seems, is less a rigid machine and more a network of interrelated events, a web of influence that does not necessarily follow a straight path. Our intuitive understanding of cause and effect, reliable as it is in daily life, cannot fully capture the subtle dynamics at play in the subatomic world. Some interpretations of quantum mechanics suggest that time itself may emerge from entanglement. According to this view, temporal order is not fundamental, but arises from the relationships between entangled particles. When particles interact, a local sense of past and future emerges. Without these interactions, time may lose meaning. Space and time, in this sense, are not the absolute stage on which events occur. They are the products of the quantum dance itself. The universe is not a clock ticking steadily forward, but a complex, interwoven pattern that produces the illusion of continuity. The philosophical implications are profound. If time is not fixed, if causality is flexible, what does that mean for our understanding of reality? Our experience of memory, anticipation, and decision-making may be deeply rooted in the probabilistic structure of the quantum world. What we perceive as sequential events might be emergent patterns within a deeper, timeless order. The past may not be entirely immutable, and the future may already resonate within the present. The classical certainty that allowed humans to navigate life with confidence is only a shadow of the full quantum reality. To grasp this, imagine standing on a quiet beach at night. Waves lap against the shore in patterns that repeat, yet never repeat exactly. Each ripple is connected to the ones before and after, forming a rhythm that is predictable at a distance, but uncertain in its details. Now imagine that the ocean itself could adjust its past ripples based on the shape of the current wave, that the sequence of events was not strictly linear, but responsive to the present moment. This is, in some ways, analogous to how time and causality operate in the quantum world. The universe is a fluid, adaptive system, not a mechanical clock. Time, in the quantum sense, invites us to release our rigid expectations. It allows us to accept uncertainty not as a failure of logic, but as a feature of reality. The past and future are not rigid boundaries. They are threads in a living, evolving tapestry. Every interaction, every observation, every act of measurement is a node where potential becomes actuality, where the unfolding story of existence chooses its form. Understanding this requires patience, imagination, and a willingness to let go of the comforting linearity that has guided human thought for millennia. The quantum puzzle reminds us that time is not a fixed river, but a flowing, shifting, interdependent network of possibilities. A continuum that may bend, fold, and ripple in ways we are only beginning to perceive as we drift further into the mysterious depths of quantum mechanics. We arrive at a question that bridges physics and philosophy. What role does consciousness play in shaping reality? In the classical world, the universe exists independently of observation. Planets orbit, rivers flow, and seasons change whether anyone is watching or not. Our awareness is a passive witness, recording events in a linear, predictable world. But at the quantum scale, this assumption begins to falter. Observation is no longer passive. It becomes a participant in the unfolding of reality itself. The act of looking, measuring, or interacting with the quantum system can influence what manifests, raising profound questions about the intersection of mind and matter. One of the most striking illustrations of this idea emerges from the double-slit experiment, where photons, electrons, and even larger particles behave differently depending on whether they are observed. When a particle is unobserved, it passes through both slits simultaneously, forming an interference pattern that suggests wave-like behavior. But the instant observation is introduced, the act of measuring which slit the particle passes through, the interference pattern collapses, and the particle behaves as though it had chosen a single path. The universe responds to measurement in a way that appears to recognize the presence of an observer. While observation in these experiments is often defined as an interaction with the detector rather than conscious awareness, some interpretations of quantum mechanics suggest a deeper connection, that consciousness itself may be entwined with the manifestation of reality. This idea, sometimes referred to as the observer effect, challenges the very notion of an objective, independent universe. If the act of observation can influence outcomes, then the boundary between mind and matter becomes porous. Reality is not merely discovered, it is co-created. The universe appears to be participatory, with conscious beings not merely witnessing events, but subtly shaping their unfolding. While mainstream science does not claim that human thought alone determines physical reality, the philosophical implications are undeniable. The lines between subject and object, self and world, begin to blur. Consider Schrodinger's famous thought experiment of the cat in the box. The cat's fate, alive or dead, hinges on the quantum state of a radioactive atom. Until the box is opened, the cat exists in a superposition of both states. The act of opening the box, observing the cat, collapses the wave function into a definite outcome. The role of observation here, whether mechanical or conscious, highlights a subtle tension in quantum theory. To what extent does reality exist independently of observation? And to what extent does awareness play a role in solidifying the possibilities? Philosophers and physicists have long debated this. Eugene Wigner, a Nobel laureate in physics, suggested that consciousness is necessary to collapse the wave function, implying that the universe is fundamentally linked to awareness. Others propose that measurement itself, the interaction of a quantum system with the physical detector, is sufficient, and consciousness is not required. Yet even within the more conservative interpretations, the fact that observation alters outcomes remains undeniable. Whether or not the mind itself is the decisive factor, the entanglement of observer and observed hints at a universe far more subtle and intimate than classical physics ever suggested. The implications extend beyond particles and photons. If consciousness can influence the manifestation of quantum events, then our thoughts and perceptions may interact with reality in ways that are subtle yet profound. Human awareness may not merely catalog the universe, but participate in its ongoing creation. Every act of perception, every measurement, every moment of focused attention may play a role in shaping the world around us, at least at the level of probabilities. This does not mean that intention can bend objects or defy natural laws, but it does imply a deep, participatory relationship between mind and matter. Quantum mechanics also introduces the concept of entanglement in relation to consciousness. If particles separated by vast distances remain linked, and their outcomes are influenced by measurement, then the act of observation in one location can instantly correlate with another. Extrapolated metaphorically, this raises intriguing possibilities that awareness might be more deeply connected to the cosmos than we realize, part of an intricate web where observation and reality are inseparable threads. The universe, in this view, is not a lifeless mechanism, but a responsive, interconnected system, sensitive to interactions at all levels. Meditating on this idea can be both humbling and comforting. It suggests that our consciousness is not a passive observer trapped in a deterministic machine, but a participant in a universe of endless possibility. Our perceptions, thoughts, and attention are not inconsequential. They are part of the dialogue of existence, a subtle but real influence within the web of quantum relationships. In the quiet of night, when you close your eyes and let your mind wander, you are part of this vast, unfolding reality, gently shaping and being shaped in return. Yet the mystery remains. Does consciousness collapse the wave function? Or is it the interaction of matter itself that brings about definite outcomes? The question may never be fully answered, because the act of studying consciousness is itself bound by the rules of observation and measurement. As we peer into the depths of quantum mechanics, we confront the limits of our understanding, realizing that awareness and reality may be entwined in ways that defy logic. The universe is simultaneously stranger and more intimate than we imagined, a place where mind and matter dance together in silent resonance. To contemplate the observer effect is to contemplate our place in the cosmos. It reminds us that reality is not entirely separate from us, that the boundaries we perceive between self and world are fluid at the deepest level. Every glance, every measurement, every act of attention becomes part of the unfolding story of existence. Consciousness is not merely a passenger in the universe. It may be one of the forces through which the universe discovers itself. In the quiet hours, as the mind drifts and relaxes, we can let ourselves linger in this thought that the universe may not be a static, objective stage, but a living, responsive process, and that our awareness, gentle, fleeting, subtle, is part of the symphony of existence. In this understanding, quantum mechanics becomes not just a scientific theory, but a meditation, an invitation to see ourselves as participants in the unfolding of reality, intertwined with the cosmos at a level far deeper than the eye can see. As we approach the final layers of our exploration, we confront the ultimate truth of quantum physics. The universe does not follow common sense. Every particle, every wave, every interaction reveals a reality that defies intuition, a cosmos that operates according to rules entirely foreign to the human mind. From superposition to entanglement, from delayed choice to the observer effect, the universe at its most fundamental level behaves in ways that are profoundly strange, paradoxical, and for those accustomed to classical logic, almost impossible to grasp. Yet, this is not a flaw or limitation. It is the very nature of existence, a reminder that the world is more mysterious, more beautiful, and more complex than our everyday experience can convey. Common sense is our mental shortcut, a map of the world constructed from millennia of survival. It tells us what is safe, predictable, and familiar. It guides our bodies, our thoughts, and our social interactions. But quantum mechanics reveals that this map is, at best, an approximation, a translation of the vast, underlying reality into forms that our senses can comprehend. At the quantum scale, matter can be in multiple places at once, Particles can influence each other instantaneously across vast distances, and events can appear to defy the linear flow of time. What seems impossible is normal. What seems paradoxical is simply how the universe is built. To accept this universe without common sense requires a shift in perspective. We must release the expectation that reality conforms to human logic, that the world operates according to the categories we find comforting. Particles are not tiny billiard balls. They are waves of possibility, clouds of probability that exist in a delicate dance until interaction or observation collapses them into a single, measurable outcome. Even the fundamental concept of identity that something is becomes fluid. Electrons are indistinguishable from each other. Photons do not have fixed trajectories. The rules that govern the cosmos are subtle, statistical, and interconnected in ways that defy simple description. One of the most profound lessons of quantum physics is the realization that uncertainty is not a limitation of measurement, but a feature of reality itself. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This is not due to faulty instruments or human error. It is the nature of the universe. At the microscopic level, uncertainty is woven into the very fabric of existence. The world is a tapestry of probabilities, a spectrum of possibilities, where the act of measuring one property inherently affects another. Certainty is an illusion. Stability is a convenience of scale. At its core, the universe is dynamic, fluid, and unpredictable. Entanglement further stretches our intuition, connecting particles in ways that transcend space and time. Two particles can remain linked across light years, responding to each other instantaneously. Action and reaction, cause and effect, locality, all these concepts begin to dissolve. The universe does not respect the boundaries we take for granted. Separation is superficial. Connection is fundamental. Every particle, every interaction, is part of a larger, coherent whole, a web of correlations that extends beyond comprehension. Reality is not a collection of isolated things, but a continuous network of relationships. Even time itself becomes flexible under quantum scrutiny. Delayed choice experiments suggest that events in the present can influence measurements in the past. Temporal order is not absolute. It emerges from a deeper probabilistic structure. Causality, so essential to human understanding, a local approximation of a more intricate reality. The past, the present, and the future are not rigid compartments, but overlapping possibilities, converging into specific outcomes through interaction and observation. The linear narrative we impose on life is comforting, but it is not fundamental. Consciousness, as we have explored, is entwined with these mysteries. Observation is not a passive act. Whether through direct measurement or interaction with the environment, the universe seems to respond to being observed. Reality is participatory. It is not merely out there, independent of us. At the quantum level, observer and observed are intertwined. The act of perception may shape outcomes, collapsing waves of possibility into definitive forms. Whether or not consciousness is essential in a physical sense, the philosophical implication is undeniable. We are not merely witnesses in the universe. We are participants in its unfolding. Accepting a universe without common sense is both humbling and liberating. It frees us from the constraints of intuitive expectation, inviting us to marvel at the unexpected, the improbable, and the astonishing. It reminds us that our perceptions are limited translations, that the familiar world of solidity, causality, and predictability is a carefully constructed approximation of a much stranger reality. Quantum physics does not aim to comfort us. It aims to reveal the truth of the cosmos, unfiltered and unbound by our assumptions. This quantum reality is not chaotic in the sense of disorder. It is coherent, consistent, and mathematically precise. The probabilistic nature of quantum mechanics produces patterns, correlations, and laws that govern the formation of atoms, molecules, stars, and galaxies. Out of uncertainty emerges stability. Out of unpredictability emerges structure. What appears to defy common sense is, in fact, the scaffolding upon which the universe builds its intricate, awe-inspiring complexity. To live in alignment with this understanding is to cultivate wonder and humility. It means recognizing that the world is far more intricate than our intuition can grasp, that every observation is an invitation into mystery, and that certainty is a convenient illusion rather than an ultimate truth. The strange, counterintuitive principles of quantum physics, superposition, entanglement, delayed choice, observer effect, are not errors to be corrected but features to be appreciated. They teach us that reality is not a rigid, mechanical system, but a dynamic, interactive, and interconnected whole, a universe where the limits of common sense give way to the limitless possibilities of nature itself. As we settle into this awareness, we begin to see the universe as it is, not confined by the narrow rules of everyday logic, not bound by the expectations of human perception, but rich, expansive, and profoundly mysterious. In the quiet of night, when thoughts drift and the mind softens, we can allow ourselves to float in this strange quantum sea, letting go of certainty, embracing uncertainty, and marveling at a cosmos that is far more wondrous than common sense could ever predict. As we draw our journey through the quantum world to a close, one truth becomes unmistakably clear: reality is far stranger, more mysterious, and more intricate than our everyday intuition can comprehend. From the unpredictable dance of particles in superposition to the instantaneous whispers of entanglement across vast distances. From the collapse of probabilities under observation to the subtle malleability of time itself, quantum physics has shattered the comforting framework of common sense.